Hello, welcome everyone in today's afternoon session. So it is an institute colloquium, and we are greatly honored to have Professor Sven-Olaf Moch, who will give us this colloquium on Toponium top-quark bound states. And before I invite him, I would like to give a brief introduction. So Professor Sven-Olaf Moch did his PhD from DAISY Hamburg on instanton effects in DIS, and after that he had done his postdoc at NICEF in Netherlands and in Karlsruhe, and since 2002 he is at DAISY Zeuthen and also a professor at University of Hamburg Institute of Theoretical Physics. And Professor Sven is of course very well known for his works on deep inelastic scattering coefficients, splitting functions. He has very seminal works on Higgs mass, Higgs boson mass, on the top quark mass, and also on the electroweak vacuum stability. So he has worked on many different areas in perturbative QCD, and he is an expert in this. And now he wants to share new excitements about his recent works on top quark bound state LHC. So welcome, and please.
Thank you. Okay, yeah, thank you for having me. Also, thanks for the very nice introduction, and also thanks to the organizers of the IMSC Spring School, an event coming now to the end after 2 weeks. It's been a pleasure for me to be here. It's been a very fruitful exchange. I've enjoyed it very much. So thanks to all the organizers for that. So as a colloquium talk, I figured I can tell something about new measurements, new developments at the Large Hadron Collider. This is an aerial view of Geneva, Lake Geneva. The LHC tunnel is basically the underground ring. We collide protons head-on at various center of mass energies, currently 13 TeV center of mass energy. And we're basically, after the Higgs discovery, we're searching for new physics. But of course, we also try to test the standard model. And the experiments, mainly ATLAS and CMS, with the multipurpose detectors have by now accumulated a wealth of data. This plot here is just for all the standard model cross-sections, which they have measured at different energies. So here you have the cross-section as a function of in units of femtobarn. And up here you have QCD, you have electroweak bosons, you have the Higgs, and here you have lots of measurements with top quarks in the final state. So this is what we'll be focusing on today. And the theory framework that we are using for describing these reactions in theory or understanding them is we have proton-proton collisions. The protons collide head-on, but protons are not elementary particles. They consist of quarks and gluons. So we pull out a quark or a gluon out of each proton, and those undergo the hard interaction, and then we observe, say, a top and an anti-top pair in the final state. And this is what's then being measured. And the master formula which we'll be using is this one here, where we have a hard scattering cross-section for two partons, I and J, which can be quarks or gluons. And they collide here, produce a final state. This is the part which we can measure which you can calculate in perturbative QCD. And then there is this part Fi, Fj. Those are distributions of functions for the momentum distributions of the colliding partons in the proton, in the incoming proton. So they basically give us an idea on what fraction of the proton momentum is then carried by a quark or a gluon when they collide. And these are non-perturbative objects, so we cannot really calculate them in perturbative QCD. We can deduce some information from them from other means, maybe lattice computations, but the main knowledge on them comes basically fitting them to experimental data. So this is the theory framework that we're using. And now when we apply this to top quark hadron production cross-sections, then we take here our hard parton cross-section and we try to be as precise as possible, including higher orders quantum corrections at higher orders in perturbation theory. So we can calculate this at leading order. We can do one quantum loop, which is next to leading order. We can do two quantum loops, which is next to leading order. And this is currently, this expansion in the strong coupling alpha S. This is currently state of the art. So we know this perturbative expansion up to those first three terms. This is what we have to work with. And then we can take those predictions. We have to choose a couple of input parameters. Of course, we have to know the value of the top quark mass. This is an input parameter into our computation. We have to choose a value of the strong coupling. This is also an input parameter here. And of course, we have to choose those proton PDFs. And then once we have all those input parameters, then we can make a prediction for what we should observe at the Large Hadron Collider. Now, before showing you what is being observed, a few more comments on the theory status as to why we can only expand this perturbative series up to the first three terms. And the reason it's simply difficult. No? So what we would like to have is we'd like to have these theory predictions as differential as possible in the kinematics that the experimentalists observe. So we don't like to have only a total cross-section where we integrate over the whole phase space, but we would like to have information, say, on the transverse momentum of the top and the anti-top, or on their pair invariant mass, or things like that. So getting these predictions at the differential level in those kinematic variables is simply very difficult, and it's been first achieved by a group of Michael Chacon, and then later it was confirmed in an independent computation by Catani, Grazzini, and collaborators, and this is now also implemented in some public code which can be used by basically by anyone. And then in order to improve upon this and make closer contact with experimentalists, one would also like to have event generation, so exclusive events at this level that experimentalists can really then compare to their data. One would also like to have additional parton shower, so this is additional QCD radiation on top of this hard scattering interaction that we have here. So on the way to the observed final states, there might be more gluon emission, which is typically encountered by Monte Carlo parton shower generators. So there are ways of how to combine those predictions with parton showers. And then finally, the top quark is not really a particle which is being observed, but it decays. Yeah? So it's being formed and then it decays, and it decays predominantly into a W boson and a B jet. And then the W boson decays again into a lepton and neutrino. So what is eventually observed is a lepton and a B jet and some missing transverse energy. And so then we would also like to have these computations including the decay of the top quark, at least in some narrow width approximation. So this is the state of the art. But there are challenges if we want to actually use those predictions and apply them. First of all, some of these NNLO codes are not easily publicly available or usable or accessible. Yeah? Some authors keep it private. This is a question then on how do you want to distribute or share your research. This would be subject of a different talk. But also from a practical side, since these computations are difficult, some of the algorithms actually require very long runtimes, numerical integrations, which can be easily few 100,000 CPU hours for one distribution. And this is actually, this is huge when you consider that you run such distributions then with fixed input, but actually in order to fit data, you'd like to have varied input, so you have to run it many times. A theoretical question which has been discussed in recent years more intensively is the accuracy of those algorithms or those the computational methods to arrive at these NNLO predictions. That has to do with providing inferred finite observables when you have to make sure that inferred singularities from soft gluons or collinear gluons cancel. And there are some intrinsic problems or biases in some of these methods here. That needs to be addressed, and what we need eventually, if we want to really compare with data, we need these predictions for a large range of mass values, say, but also for other parameters varied. We need to vary the Parton distributions as an input also, and this is why we had 2 years ago, we had provided us with a customized version of one of those codes here, which we could then run in order to do a phenological study, and also interfaced it then to some library which provides grids, so that once we have done a computation, we can provide grids with the results of those computations to other people, and they can then reuse them and they don't have to run the program again, because this is then the way to share research. Right, and if we are doing this, then this is the result what we get on a theoretical level. On the left-hand side, you can see the cross-section for TT bar production differential in the pair invariant mass of the top quark pair. So you take the top quark, the anti-top quark, you calculate the pair invariant mass, and then you can bin it as a function of MTT bar, starting off at the threshold, roughly 350 GeV, and then going all the way up to very high, up to 5 TeV roughly. This is the theory prediction here. And these two plots here, so the green line is basically from our computation that we have arrived, and the lower ratio is then checking it with previous computations and then seeing that within an uncertainty of about 1%, we are agreeing with previous computations. The right-hand plot is the same for the rapidity of the top quark pair. So you take the top quark pair, and its rapidity is basically giving you the polar angle with respect to the beam axis as to where you see this in your detector. This is also an observable that experimentalists like very much. And also here we agree by and large among those different computations by about 1%. Yeah? Well, just tells you this is the current accuracy that we can reach at the in QCD in strong interactions for those codes, and there is certainly room for more improvement. Yeah? This is another plot where we have basically checked validity of our codes. This is then giving you an idea again for the MTT bar invariant mass distribution, comparing our predictions and then comparing this with uncertainties with the previous prediction within their uncertainties. And then you also see that while for low invariant masses, you have about 1% uncertainty that increases dramatically when you go to the TeV range here, because the cross-section goes down. In order to get good precision there, you would need to run your Monte Carlo integrations for much, much longer times, which is very costly. So those are the challenges that we face there, but we have overcome them. And then we can compare to data. There is plenty of data by now on top quark pair production from the LHC, both from Atlas and CMS. And they are classifying or categorizing their data into what final states they observe. So as I said, the top quark decays into a lepton and a B-jet and some missing energy. So then the experiments, they look for final states where they see either 2 leptons, which they can then associate with the top quarks, or they see 1 lepton and 1 jet. This is then either dileptonic or semileptonic, or they see only jets, which would be an all-hadronic decay channel here. And then we have total cross-section measurements, and we have double and triple differential measurements, predominantly in the invariant mass of the top quark pair and the rapidity. And if you look at the number of data points, this is over 100 different data points in all these bins. So this is a huge amount of data which is being accessible right now, and we can compare it with theoretical predictions. This is for basically the whole history of the LHC now. In the very early days, the LHC started running at 7 TeV, and it also had a run at 5 TeV center of mass energy. Then it was upgraded to 8 TeV, 13 TeV, and now 13.6 TeV. And you see that across all these center of mass energies, we get very good predictions for the total cross-section here that have been measured by both Atlas and CMS. And the color codes is using different input for those Parton distribution functions, which is one of the input parameters that has to be varied, and you see that by and large, within experimental uncertainties, you have very good agreement with data. Now, if we go more differential, then this is one example for the rapidity distribution of the TT bar pair. So the detector covers basically rapidity values between 0 and 2 point, a little bit over 2 in various bins here. And then the individual columns are then looking at bins in the pair invariant mass distribution. So the first bin goes from 250 to 420. So it's a rather wide bin. And then you go up to the last bin is from 1 TeV to 3 TeV. So in all those bins you have data. And you see that those theory predictions using, again, different PDF sets at input, they do largely a good job, some better, some worse. And we can quantify the agreement with data by making a chi-squared analysis. So we had of the order of 120 data points. And you see that within uncertainties, all these sets, they roughly give you a chi-squared value of 1. So we claim that this part of the data we understand and we are in good shape. Huh? What can we do with this data? Now we can extract the top-quark mass, for example, as a parameter. So it's an input in our theory computation, so we can leave it as a free parameter, and we can see what's the best fit value if we determine it from the experimental data. And those plots here, these are different combinations of data, and then extracting top-quark mass value. So if you fit the top-quark mass to any of the individual data sets that I had in the table before, then you see you get a varied range. If you combine, for instance, all CMS data, you get a top-quark mass of 171 GeV. If you combine all Atlas data, you get a little larger top-quark mass. Or if you combine them via the final state decay signatures like dileptonic, all combined is a top-quark mass of 170.7 GeV. Semileptonic combined is a little bit larger. So you see there are within uncertainties, there's not quite overlapping within 1 sigma uncertainties, but there is also not a really great tension. So it's all compatible within roughly 2 sigma uncertainties. And the top-quark mass is interesting because we can use it to make statements about quote-unquote the fate of the universe. If we look at the entire standard model and we look at the electroweak sector of the standard model and we look at the way the self-interaction of the Higgs particle is driven, then the self-coupling of the Higgs, of course, is also running with the as a result of the quantum corrections. And if we require the self-coupling of the Higgs, call it here lambda, of mu r to remain at least positive definite over a large range of scales, and we can basically take it up to the Planck scale. If we demand positivity, then we can look at the beta function for the running coupling, for the running self-coupling of the Higgs, and we can look at the driving parameters in order for the positivity here to be remaining. And the driving parameters are actually the top-quark mass and the strong coupling constant alpha s. And in combination, for the Higgs self-coupling to remain positive all the way up to the Planck scale, we can phrase this into an inequality as a bound on the Higgs boson mass. So solving this to NNLO, including electroweak corrections to NNLO that have been calculated by these people here, this reasoning tells us that the Higgs boson should be heavier than 129.6 GeV with an uncertainty, which is given by the difference of the pole mass that we're actually measuring minus a reference value, which has been chosen to derive that number here, minus some other uncertainty depending on the alpha s value that you're taking, minus the reference value here. And then you see in particular the lighter top-quark masses that we've seen on a previous slide. So 171 or 170 GeV here, they give us a negative correction to that bound. And as you know that the Higgs mass has been measured to pretty precisely 125 GeV. We basically need to be able to subtract roughly 4.5 GeV from this equation. But the difference in the measured top quark pole mass, say 171 GeV minus 173.3 GeV, this is precisely in the right ballpark, so that this inequality or this bound on Higgs mass can actually be fulfilled all the way up to the Planck scale. And this can be coded, or has been coded in this colored plot here, where we have, as a function of the Higgs mass, we have the top quark mass, and then in this plane we can put in those bounds. So a stable electroweak vacuum would basically be one where you have a stable absolute minimum, meaning that the self-coupling never turns negative. And this is then given by this green area here. So we are seeing that with Higgs of 125 GeV and a top quark mass of roughly 171 or so GeV, we are okay. If you allow the self-coupling to be slightly negative at very large scales, then we would have our potential, our Mexican head potential. So we would be sitting somewhere in the minimum here, then it rises, but somewhere at very large scales, it turns slightly negative. Then we would not be in the true minimum, but we would be in a false minimum trapped. We could, in principle, move to the true minimum at very large scales, but a potential barrier which is between us and a true minimum is so large, or actually the tunneling times that it would take to actually reach this true minimum are so large that they are estimated to be larger than the age of the universe. And this is what is called then a metastability situation here. So this is this orange line here. And then with these estimates on tunneling, on a negative self-coupling, and the tunneling rates towards the true minimum, then we would say at very large Higgs top quark masses of the order of 177, 178 GeV, would then be really decaying too fast, and so this would not be a stable situation for the standard model electroweak vacuum, and then there would probably be a strong indication to no physics. But interestingly enough, we're sitting here right at the boundary with the measured values. So this ABMP16 number is some number that we had determined some time ago. We're sitting right at this boundary here between stability and metastability, and this is extremely intriguing. And this is a plot now of the running of the Higgs self-coupling for a chosen set of parameters, Higgs mass, top quark pole mass, alpha S. And you see with a top quark pole mass of 170 GeV, you're kind of within uncertainties. You're going slightly negative at the Planck scale, but within uncertainties, it's all okay. And this would basically be the situation where we have here slight metastability, but actually it would not be any strong indication for new physics. So this is telling you why this whole top quark sector is very interesting, and why there's also a lot of motivation among the experimentalists to determine the top quark mass as precise as possible, so that we can make a decisive statement on the fate of the universe, if you wish. Yeah? Right.
So where does this central value come from? So
that one was one that we had determined using less top quark data some years ago, and we came up with 170.4 GeV. Yeah?
And that's different from the CMS and Atlas.
So CMS combined, for instance, gives you 171.1. Yeah. Atlas gives you a bit larger value. And then here, depending on whether you look at dileptonic or semi-leptonic final state, you get 170.7, 172.2. So this is basically the range of values that we are looking at. Yeah.
And what might be the reason for the difference between your, value for the
between
top-quark
our
mass? Yeah.
so we used less data. Using more data, we do get a slightly larger value, but not by much. But it's also the question on the correlation of that value with the other input parameters, because you also need to see it's correlated with the value of the strong coupling that you're using with the proton PDF. So if you make a fit to this data, in order to really capture the full uncertainty, you need to take account for the correlations among all these parameters, and the top quark mass is just one. If I were to fix alpha S in the PDFs at a given value, I can extract any top quark mass you would like me to have, yeah, simply because there are correlations. So this makes it also a bit tedious, since we have to really account for all the uncertainties if we want to give you an honest uncertainty on the numbers that we're extracting. Sorry? Right. So we exactly. So we get roughly 115. We get here. This is a bit smaller than what is typically been quoted as the world average. And also there are reasons why, for instance, we get this as a preferred value from doing a fit. Other people get other values. So this has to be accounted for. You see, if you go back to the slide here, the smaller value of alpha S is basically pushing up the bound again. So you see already in this bound, a smaller top quark mass is lowering the bound, a smaller alpha S value is pushing the bound up. So you see this type of correlations there, and you have to account for it, and you have to simply quote the uncertainties that you get from keeping all the correlations. But also alpha S determinations is an active area of research. Just for this question, the top quark mass is actually the driving quantity. Okay, so let me come to new top quark data. So there is now, since roughly last fall, there is a new measurement by CMS that is currently being published, and it was motivated by direct searches for new physics in the standard model. So in particular for looking for the direct observation of new heavy scalar bosons, which would decay into top quark pair. And so you can think of this as basically gluon-gluon fusion. They would go via top quark loop into some scalar, new heavy scalar, and then this scalar would again decay into top quark. So this is the leading order diagram that you can look at. And then they have been asking themselves the question, could we either look for a scalar boson or a pseudoscalar boson? And then you can describe those this new physics. You can describe with an effective Lagrangian with a Yukawa interaction. So you have your top quark pair either coupling to a Higgs boson with some coupling strength, or the top quark pair in a pseudoscalar combination coupling to a pseudoscalar with a pseudoscalar coupling. And so on top of what I've been showing before, what the CMS has now achieved, they have achieved the reconstruction of the invariant mass of the TT bar pair, but they've also been additionally able to measure more differential variable of the final state. In particular, they have been able to measure or acquire information about the spin of the top quarks. And this they were able to do so by looking at the unit vector of the lepton momentum of the two leptons. So top quark pairs decaying W, then lepton and a B jet, and also W, lepton and B jet. So looking at those identified leptons in the final state, and then looking at the scalar products of those two lepton momenta from the final state, boosted in the relative into the respective helicity frames. And then you can take them in one combination, or you can flip the one lepton vector, and this gives you two measured variables, which CMS called C-hel and C-han, which basically contain the spin information on the final state. And with that, they have been, first of all, information on the spin of the final state, and then they can reconstruct the MTD bar final state. And from the spin information, they have been showing that they can, for instance, distinguish between a scalar and a pseudoscalar resonance in those variables that they are plotting here. So this is a normalized cross-section as a function of this this C-Hell variable, where you just take the unit lepton vectors here in a scalar product. And since this is basically an angle, if you wish, cosine of an angle, it goes between -1 and 1. And you see that for a scalar, you have a particular shape. For a pseudoscalar, you have basically the opposite shape. So by measuring this, you have good discrimination power in looking at the spin, at the parity of this of the scalar boson. Yeah? Okay, and as I said, they also now are able to reconstruct the invariant mass distribution, and compared to what I've shown you before, what you see in those plots here is that they have now much finer bins in a pair invariant mass of the top quark pair. So between the threshold at 350 and around 1.5 TeV, you see they have of the order of roughly 20 bins in the MTT invariant mass, and so they are now able to have a much finer resolution, in particular of the threshold region. And this is the absolute, this is the number of events which they have there for different, basically in different angular bins of the cosine of the top quark scattering angle. And then what you see here, as you go close to threshold, they observe there is an excess of data near threshold, which is, you wouldn't see from this plot here, but basically in the ratio to the background and then estimating the background as precisely as possible, they saw this excess of data. Now the question is, what could it be? Of course, in this hypothesis that they're searching for new heavy bosons, they came up with this plot here, which is a constraint on the pseudoscalar coupling. So as a function of this hypothetical pseudoscalar mass, which could have a mass somewhere between 360 and a TeV, they came up with this plot here for the expectations, which is 1 sigma and 2 sigma is this green and yellow bands here. And they came up with a blue area for the observed limits on this on the pseudoscalar coupling, which would then fill up or account for this excess. In particular, at low values of the pseudoscalar mass, you see that there are these deviations, so that goes into direction of a pseudoscalar hypothesis here. So for the scalar, they wouldn't see this, so they see this particularly for the pseudoscalar. But before judging that there is new physics now, and we have seen a pseudoscalar new Higgs boson, we have to look a little bit back at heavy quark production near the threshold. And there it's good if we just look at the quantum numbers that we can assign to a final state TT bar pair in some spectroscopic notation, where we look, where we classify all the TT bar states by whether they are by their orbital angular momentum, whether they are an S wave, whether a P wave, by the spin which they can have. So the TT bar pair can be spin singlet or spin triplet, and by the total angular momentum, and also by the color which they carry. So this can be color singlet, color octet, and so altogether we can write the TT bar pair with all these quantum numbers in a spectroscopic notation as something like orbital angular momentum, and then lower indicator total angular momentum, color singlet, color octet, and the spins we can indicate. Yeah? And so this is the one thing, and then we have to look at the kinematics close to the production threshold, because close to the threshold you just have enough energy to produce a TT bar pair, but they will not be flying very fast away from each other. Yeah? So they'll be very slowly moving at the scales that we are talking. That means they have a low velocity. So in terms of the mass and the protonic center of mass energy, we can write down the heavy quark velocity as this beta, as the square root 1 minus 4m squared over s, and this is small. Yeah? Close to threshold, this is a small number. Yeah? And then we look in the spectroscopic notation at the bond cross sections that we have, for instance, producing the TT bar final state as an S wave. Yeah? and then the cross-section goes with the power of beta. If we had a p wave, then the cross-section, the bond cross-section goes with the power of beta cubed. Huh? So this is basically, you work out the leading order cross-sections and you get them. Then once we include gluon radiation or quantum corrections due to gluon exchange, gluon loops, then there are two types of corrections we have to account for on top when we look at the quantum correction. So keeping this heavy quark velocity beta as a small parameter, we discover that there are so-called threshold logarithms. Those are Sudakov logarithms from the soft and collinear emission from a gluon, from a heavy quark. And parametrically at each order in perturbation theory, so we have alpha s to the power n, and then they come along with large logarithms of this small parameter beta, and they basically can come with double. These are double logarithms. So at alpha s they can come up with a log squared and a log. At alpha s squared they can come with a log fourth, log cubed, log squared, and log, and so on. So they are large. They can be resummed to all orders in perturbation theory, since we know how soft and collinear radiation factorizes, but they're simply there. So we have to deal with them. So this is one class of corrections that we have once we account for quantum corrections. The other interesting class here is the so-called Coulomb corrections. Namely, I can have this top-quark production, say, from gluon-gluon scattering, and then they form a TT bar pair. And if they're moving slowly, if they're, say, non-relativistic, then they can have gluon exchange between them, say one gluon exchange, two gluon exchange, and so on and so forth. And they come up with inverse powers of the small parameter beta. So you have alpha s to the power n, and then they can come with inverse powers of beta to the power n and lesser powers at each order in perturbation theory. And they are called Coulomb corrections.
This is the parameterization, right? Because if you're at small x, then you need to look at s hat rather than s.
When I'm where at?
No, for the beta, because you have 4m squared by s, but actually the threshold will depend on s hat rather than s.
Right. So this is, think of this as the partonic center of mass energy, yeah?
Okay.
Which is actually
so
probably
s is actually s hat, or it is s?
So
So
for
it's
the
more like a parameterization, right?
exactly. So for the considerations here, we can think of it as the partonic center of mass energy, but equally it also applies to the full hadronic center of mass energy. Yeah. So once you stick it into convolution, then you have to go from S hat to S. Yeah.
Okay.
Yeah. But I'm making just a discussion here on a parametric level. Yeah?
Okay. No, that's right. Yeah.
And the Coulomb corrections are basically those that you know already from electrodynamics. When you have a positive charge and a negative charge, you have your Coulomb potential between them, and it tells you this is attractive. And basically the same thing we are seeing here. So in quantum electrodynamics, you would have an electron and a positron. You can exchange one photon between them, two photons. And if you calculate this, then you're basically getting precisely the same type of corrections here. And now we are in a strong interaction theory. We have color charges. Gluon force is the gluon is the mediator of the force between them. And we can have as many gluons as we need. And this is then providing us with an interaction between those final state particles. And as I said, it's of a different parametric form than what we typically have from the real emission of gluons, like when we have a gluon somewhere, some real soft and collinear gluon emitted here. So
given the top-quark lifetime, it's only a small exponential tail for which this one is relevant, or what? I mean, the top decays.
Right, so the top decays before it hadronizes. On the scale of the top lifetime, it's a relevant correction. So I'll have a plot on this in a minute. Yeah. Right. So if we combine these two quantities, then we see we can write the partonic cross-section as something like Born, and then we basically sum over all the Coulomb corrections, alpha s to the power k over beta to the power k, and we can exponentiate all the soft radiation. All these logarithms of beta we can resum in some exponential. So this is the parametric form of the all order partonic cross section that we have, and then we need to convolute with PDFs. So we have our parton luminosity. So this is then convoluting those betas in the appropriate variables. And if we look at the differential cross section now at a hadronic level, where this is now the hadronic center of mass energy in the beta here. If we look at it at a differential level, then we have 1 power of beta coming from phase space. We have our luminosity here, and then we have our partonic cross section also parameterized in beta. And then we can do a power counting. We get for S-wave Born cross sections, we have basically 1 power of beta. We have 1 power of beta from the phase space. So if we look at this differential cross section at the leading order, we would say this scales as beta squared. But now we go to next to leading order, next to leading order, and we keep picking up these Coulomb corrections here. So then doing power counting at n cubed leading order, we see, okay, our leading contribution to the cross section would scale as 1 over beta, which is still integrable if you wish. But then as we go to N4LO perturbation theory, we start to encounter 1 over beta squared singularities, which are no longer integrable here. Yeah? So we see already from this power counting that there is a breakdown of perturbation theory as we include both these Coulomb corrections and the threshold corrections. So we have to do something else. Yeah? And something else is we basically have to resum them in non-relativistic QCD. I'll explain you in a minute how that works. I just want to say this is a topic where already much work had been done before, especially in the context of a future E plus E minus collider, because there you would be in a favorable situation that you have E plus E minus colliding, and you can tune the center of mass energy. And you can tune it precisely such that you are not only at the Z peak where you would see a resonance, but you could also tune it that you are at the TD bar production threshold. So you'd then be able to see TD bar resonance there forming. So your E plus E minus collider at 350 GeV center of mass energy would be a perfect machine to actually do precision studies of this phenomenon. And since Coulomb corrections are a universal phenomenon in quantum field theory, those investigations or those effects would also apply to other charged particles. And some estimates have also been made for an E plus E minus collider. When you have a W plus and a W minus boson in the final state, there should also be photon exchange between them as a way of Coulomb interaction. And there also estimates have been made, but in comparison to QCD, those effects would only be in a per mil range. Yeah? And now we are talking this effect at the LHC, where some years ago first effects have been quantified, and we had written a paper on that many years ago. But now with more precise data from the LHC coming up, there are many more studies basically in the last 5 years in this area. And the extension of the theory framework that we have to do is we go back to our master equation here. And we're interested now in, say, producing S-wave TD bar pairs as color singlet or color octet in the appropriate spin states close to threshold. So then we have to apply non-relativistic QCD, which is yet another factorization on top of our master equation, because now we have to take our hard partonic cross-section and we basically factorize it into 2 functions. One is the free production rate of a TD bar pair. And then once we have the TD bar pair, we have to account for the potential effects. So we have to account for a quark here of one color charge, other quark here of other color charge, and we have to account for the potential. So this is This is then the QCD potential that can be calculated. And then we have to simply determine the Green's function as a solution to a normal Schrödinger equation, where we use, instead of, say, potential for QD potential, which gives you then the hydrogen atom, we use the QCD potential, and we try to get the Green's function, which then describes the interaction of two heavy quarks. And this is then multiplied with our free production rate, and this is then summarizing or resumming all these potential interaction effects to a given order in perturbation theory, basically to the order that we know the potential and that we can solve the Schrödinger equation here. No? And we can do this in differential kinematics, so we can do this precisely in the variables that are being measured by the LHC experiments. And on top of this Coulomb effect resummation through the solution of the Schrödinger equation, we can also resum all soft and collinear emission that I had shown before. So we can basically put in all the different resummations of all effects and get the best possible prediction. And then once we do this, this is the result that we get for the LHC now at 13 TeV center of mass energy, invariant mass distribution for the top-quark pairs. Now this is plotted for top-quark invariant masses between 330 and 380 GeV, so zooming in on the threshold region. And this is for the three dominant S-wave channels, so we can have the gluon-gluon going to a TT bar pair, and then this is an S-wave, spin singlet, color singlet, or we can have the gluon-gluon going into TT bar pair with an S-wave spin singlet but color octet, or we can have a QQ bar pair going to a TT bar pair as an S-wave, color octet, and then spin triplet here. And then when we look at those dominant channels, then we are basically seeing if you have the TT bar pair as a color singlet in the final state, then you have the same as you have in QED. And you see that there is an attractive interaction between the quark and the antiquark, and you get a nice enhancement here. This is this red curve here. So this would be gluon-gluon going to TT bar S-wave singlet here. And this is giving you this enhancement. Whereas if we have the TT bar pair in a color octet configuration in the final state, you have this gray curve here, and this is repulsive. So then there is a repulsive interaction. You can actually see this going back to the QCD potential for a color singlet or a color octet state. It's either attractive or repulsive, and you see this in these two plots here. Either you have an enhancement or you have a depletion. Now threshold in fixed order perturbation theory would be at 344 GeV, so it would be right here. But now you see, due to this attractive interaction between the quark and the antiquark, you're basically lowering the production threshold. So the onset of TT bar production is already a few GeV, say 5 to 10 GeV below the actual partonic threshold, as you would naively think. Yeah? And this is coming back to your question. So with a top quark decay width of say 1.4 GeV, this is relevant at this scale here. Yeah? So you see that there is actually this small enhancement, and this is not captured by standard perturbation theory or any parton shower Monte Carlo, which the experiments are using typically. Yeah? And this is moving on, looking at scale uncertainty. Basically, the blue curve here is adding the color singlet, color octet. This is the blue curve here, and then we can do fixed order perturbation theory, or we can do resummation. So these are different variants on treating the soft emission here. What I should note that all the other channels where you have like gluon-gluing going to an S-wave spin triplet, or QQ bar pair going to spin singlet, or quark-gluons, they are all rather small, and they sum up to something of the order of 5%. So for the discussion here, we can basically neglect them. Yeah? Right. So basically, when you solve the Schrödinger equation here, so you solve for the energy, and the finite width of the top quark adds an imaginary part here. So basically, this is a function of E and plus I times the decay width of the top quark. Yeah? So this is something you have to put into the Schrödinger equation here.
The width of that, the curve that you show, that is related to this gamma t, or is that?
So gamma t is basically a parameter which determines the width of course of this peak here. Yeah?
But is it a few times gamma t, or is it like many times gamma t, or what?
I mean, you see, this is like 140. So this is each tick is 1 GeV. So you see that the width of this peak here is 2 to 3 times gamma t. Yeah?
I see. Okay. And it's proportional to that. If gamma t comes down, this one also becomes sharper.
When you look at something very wide, of course, you would smear this out, yeah, and you would flatten it, yeah, absolutely. But since gamma t is well measured, this is an input parameter which we can simply take and which has a negligible uncertainty for those studies that we do here.
Okay.
Yeah?
Thank you.
Yeah. Now the question is, since I said this is not really included in the experimental analysis as a background, and so if we want to explain some excess of observed data over background, then we have to go back and we have to ask the experimentalists, so what did you really put in as a simulation into your simulation? And this is shown in this plot here. So blue is basically our prediction here, and which is accurate to next to leading order and next to leading logarithmation based on NRQCD. And the red curve here is what the experimentalists have used. So you see it basically has a sharp drop close to the threshold. And then here at large invariant masses, it has been rescaled to the next to leading order QCD predictions. Yeah? So you see that there is basically some gap between what you get when including Coulomb corrections and what experimentalists have been using. And so our proposal was then to them was that they should basically use NRQCD, non-relativistic QCD predictions for MTD bar invariant masses below 350 GeV. And then you see that there is a nice region where the predictions overlap, and then for MTD bar values above, say, 350 GeV, when you're further away from threshold, you can then take standard fixed order perturbation theory, improved with parton showers, and you name it. But really close to threshold, this is precisely the additional information that you have to put in. So for large MTD bar, the pink curve would be better because this is exact to next to leading order, whereas our NRQCD approach here should be chosen at low scales. Yeah? So this is basically some overlap region where we would propose just do the matching there. Of course, this is a pretty crude way of doing matching. We know that when you combine different theories, you should also do matching computations by expanding the different theories in this limit and then doing an overlap. But this is future work, so at the moment, just to give the experimentalists something that they can work with, this is our proposal, just do it like this. And we also know that our prediction here for large MTD bar invariant mass, the blue curve can be improved by adding the next order and perturbation theory. So we know this and we've checked this. Yeah. Okay, and then going back to the experimental analysis. So when they now test again the coupling strength of a potential pseudoscalar boson, now including in their background estimates also the effect of, in particular, of the dominant S-wave color singlet bound state, then you see that the blue area, which is the observed part, and the yellow and green band, which are the expectations for these couplings, they nicely match, and there is basically no room for or immediate urgence for demanding a pseudoscalar to explain the access of the data. Huh? And with this, with the signal strength and the measured spin dependence, the experiments, so CMS can also nicely distinguish between a scalar resonance or pseudoscalar resonance. So if you go for a scalar resonance here with the experimental uncertainties at 1 sigma, 2 sigma, and 3 sigma, you would be observing something like this here. And if you go for a pseudoscalar resonance, then you see this is really favored. This is really favored for the this is really favored by the experimental data. So a signal strength of 1 for a pseudoscalar is what comes out of the data simulation. So such studies then can also tell us that an observed pseudoscalar resonance is compatible with the TT bar pair in an S wave. So this gives us a consistent picture.
Why is the TT bar, the NRQCD, why is it like a pseudoscalar?
Yeah, it's a pseudoscalar.
Why is it like?
You have when you do the spin projection on the T and the anti-T, you have a gamma 5 for the different spin orientations, and this gives you pseudoscalar orientation there. So if you work out the projections, it basically requires going through all these states here with all these quantum numbers, and then you see that the S wave spin singlet, color singlet, this is pseudoscalar.
I see.
So
But the octet would be.
sorry?
The vector will be much heavier though,
Yeah.
and even less likely to go.
Right. Yeah. So basically, so including QCD bound state corrections for the top quark, these Coulomb corrections, then basically provides agreement between data and theory. The parity can be established of that object that is being added there, and with that, yeah, I come to an end. This is basically ongoing measurements. So at the moment, this has been observed by CMS. Atlas is still trying to improve their analysis. I'm sure during the year I will also hear from Atlas on this. I take this as one interesting example of LHC entering the precision era, because I would not have thought that such precise measurements become possible, but we see them now. Top-quark hydroproduction is an interesting area where you can get a lot of information, even on big questions like stability of the electroweak vacuum. And to model these toponium bound states, Coulomb corrections have to be taken into account. They're at the current level of precision non-negligible, and one has to, on a theory side, but also on the experimental side, still work hard in order to improve both predictions and measurements. But I'm very optimistic that this will be an interesting area of future developments. So thank you very much.
Thank you, Sven, for this very nice colloquium, and time for questions.
Just a comment on vector. Vector, I believe, should be more closer to the pseudoscalar itself, because you can actually take charmonium and bottomonium. Basically, vector and pseudoscalar are related by hyperfine splitting, and it basically goes inverse with mass. So I would naively expect at very large mass, they basically becomes more and more degenerate. So you can take charmonium, which is 113, and bottomonium, it is some 60 acres. Ground state is still pseudoscalar, but pseudoscalar and vector will be more near to degenerate in the top quark sector. Is what I believe.
So basically, at the moment, we're just looking at those dominant S-wave channels. Of course, you can then extend this to P-wave, so you'll basically have a whole zoo of different of states with different quantum numbers. And as I said, those states which we have neglected here so far, even among the S-wave states, they contribute with a small percentage. P-wave states have an even smaller contribution. So some of them, we've calculated some of them. It's for the bulk of the picture, they're not relevant here. No? So the thing is really what is driving is this pseudoscalar bound state of a TD bar S-wave color singlet.
Between color singlet, color octet contributions to like JPSI and Upsilon. So is that settled now? Is there anything that?
So there is the difference there is, so here we can basically, we calculate this and then the top-quark decays. So in germanium or bothonium, you're sitting at low scales, and so then you have to augment your factorization ansatz with some non-perturbative long-distance matrix element, which then captures the effect whether you have color singlet, color octet, and there is still some. They're not all well determined, and especially for the color octet, there is still. This is active research, also improving theoretical predictions and fitting to more data, because some models work, but then if you include spin degrees of freedoms, color octet model for long distance matrix elements again doesn't work. So there is still a lot of work as well to be done there. So here we are in a little bit simpler situation because we don't have this long distance hadronization part here.
On the screen that you had, just a minor point. Normally you write E plus I gamma by 2, right? This is just nitpicking, but
what do you want?
usually the width you write half width, right? Gamma by 2. I mean E plus I gamma by 2.
Okay,
right?
okay, yeah.
So this is
okay.
just scaled. I mean, okay.
Okay, right.
Nice. Okay. Thanks.
I have a very naive question. So while in doing these analysis with these new physics, the H or the A, do we need to consider the interference effects with the standard model like diagram, like at high energies when, like will the interference between the new physics and the standard model diagram also contribute to the new physics?
Right, so this is a very good question. So I skipped that part, but of course so I come from standard model the standard model background. There are people who spend career on searches for new physics, and now the counter argument from people looking for new physics is that what you should actually do in an experimental analysis, you should take those diagrams and look at the interference of those diagrams with the standard model ones. So look at the interference of a pseudoscalar with any normally produced TT bar pair. There are also publications now written on this. I think this is certainly the right question to ask and also the way to go. Since this is at a very early stage, I'm just giving you a coarse-grained view on this, but for improved experimental analysis, this is certainly the way to go. What I should say maybe is it also depends a little bit on the accuracy of the experimental data. So this is now the run 2 data completely analyzed. So this is 138 inverse femtoband from run 2 at 13 TeV. This will certainly be repeated with run 3 data. So as we accumulate more statistics, I'm sure this picture will also be refined on that side, and would then be also more compelling argument towards doing such studies.
Contribution and the color singlet contribution here with a phi. Will they interfere?
Yeah, sure. I mean, this could be any scalar which you which you have there. Sure, this.
Okay, there's Higgs contribution.
So one question here. So in the slide number 27, you said about this repulsive interaction. Could you explain that part? This repulsive interaction.
Right.
Could you explain that part?
Why it's repulsive?
Yeah.
So basically, you can calculate the QCD potential, and you can take two quarks, and you can take the exchange, the gluon exchange between them to be color singlet. You can take them as a color singlet, or you can take them as a color octet combination. Yeah. So you can, QQ bar. You have those two possibilities, and then you calculate the QCD potential for those two color configurations of the QQ bar pair, and then you find that for a color singlet configuration, it is attractive, and this is basically same as in QED, and for color octet, it is repulsive. So it has a minus sign, and then this repulsive interaction you put in here, and this gives you then, if you solve the Schrödinger equation, this gives you then this depletion of the region close to threshold. So there you don't pick up much from the color octet configurations, but then as you go to larger antidebar invariant masses, they start to rise quickly, whereas the color singlet kind of stays constant here. Huh?
Thank you.
So at the very beginning, you showed some invariant mass plot. So your result and some other previous known result. So there are uncertainties. So what I see that previous result, the uncertainties is high, and in your results.
You mean here?
Before that?
Here.
No, before that, some invariant mass.
Ah, here.
Yeah, here.
Yeah, this is basically checking the validity or accuracy of our NNLO differential distributions, and just showing that we get them exact at 1% precision. Yeah? And within that uncertainty, we are agreeing with previous computations. We could try to go from 1%, say, to 0.5% precision, try to decrease this, but then this would require much extended running times of our Monte Carlos. So in order to produce all those predictions that we had to use here, we already required more than 2 million CPU hours. So it's a massive amount of computing that you have to do there. And then on top, if you go into the details of those subtraction schemes, then this code we are using here, this is relying on phase-space slicing. And there are some questions with power corrections that can spoil the accuracy. And we have the suspicion that we might have some intrinsic bias of the order of 0.5% to 1%, which we cannot overcome due to the method of calculation there. Yeah? So this seems to be an intrinsic limitation on our side, and it would basically need a new NNLO parton level Monte Carlo for that to improve, which is then not using any of these phase-space slicing schemes, but local subtraction.
So this uncertainty is from the subtraction scheme.
Subtraction and Monte Carlo integration. Yeah? So all combined.
And from, in your computations, those uncertainties are much lower than the previous calculations.
I would say they are of similar,
but in the
size.
Plot, in the plots, they are much lower.
So here it seems that we have smaller uncertainties, but due to those power corrections in the slicing scheme, which haven't been quantified, we don't argue that we get better precision than 1%. Yeah? So this is from all the ways we have looked at it, we would say we can do this accurately to 1%, but not beyond. Yeah? So if you want to have per mil level predictions for top-quark pair production at the Large Hadron Collider, then this is basically an entirely new project to be started.
I have another very naive question, but maybe I'm going way ahead of what is being done now. So, if such an analysis is being done is done for the case of a future circular collider, then would top PDFs become important? Could the tops be important in the initial states for an FCC 100 TeV, for instance, say?
So at the 100 TeV collider, so typically I would argue that an intrinsic quantum degree of freedom of a new heavy quark should only be relevant at scales, say, 10, 20 times above the threshold. So then you take top quark 170 GeV, you would say 100 TeV collider, you might be at the margin of this becoming a relevant concept. Yeah. But we also see that even if we are sitting at high scales and we take PDFs which don't have this degree of freedom, then we still can get a good fit of data, because I mean the sum of all momenta in the proton has to be 1. So there is a sum rule, and then if you have a new heavy degree of freedom, you're basically generating it from the gluon predominantly, and so there is a balance then between those. There is a balance in the momentum sum rule, and so there is no direct, I would say, no direct gain or big change if you suddenly allow for top-quark PDF.
Any further questions?
So the VQCD that you had, that is a calculation. You compute the non-relativistic limit of QCD. Is that how you get that, or?
In principle, yes. So and basically, you can when you write down your any Feynman diagram, you can make an expansion in beta here. Where do I have it? So you can make an expansion, systematic expansion in beta, and then you can derive from any perturbative QCD Feynman diagram, you can arrive at what you get in the non-relativistic limit, and then you can work with it. Or you directly take the QCD potential and you apply Schrödinger equation, and then you're done. But there is a way of actually deriving it.
What do you mean by take the QCD potential? Is that?
I mean, this is the QCD potential here that has been calculated. So as I said, you take a QQ bar pair and you look at the gluon interaction and you simply calculate it. Yeah. So calculate the quantum corrections like you would do when you do quantum electrodynamics, 1 photon, 2 photon, and so on and so forth. Yeah.